going to talk about 3-1 guided polynomial, not guided, graphing polynomial functions. They are guided notes. Our objective is that we can predict the behavior of polynomial functions. So what is a polynomial? What is a polynomial function? So we are looking at graphs and functions that have exponents that are whole numbers. So no negative exponents, no fractional exponents. So one definition would be f of x equals x to the n and then plus x to the n minus 1. So we would decrease our exponents plus x to the n minus 2 and so on all the way down to just a number like b, right? And then also our exponents. So this is a sub n minus 1. So that, not exponents, coefficients, the numbers in front of x squared will not be imaginary numbers. Okay, they'll just be real numbers, and so nothing weird, but we won't have negative exponents and we won't have fractional exponents. Standard form is taking that highest number and putting it in the front. So if this is a 7, this would be a 6, this would be a 5, and so on. If this is 11, 10, 9, so on. Okay, so we don't care about the coefficients in that case. We are just targeting the exponents. So we want our powers, our exponents, to go from highest to lowest when we put a polynomial in standard form. Okay, and when we pick out these key features of a polynomial, we want to make sure that our function is in standard form before we pick out these key features. So there are important things. These two kind of go together, the degree and the leading coefficient. If the degree is odd, it's going to act like a line does with its end behavior. Right, so let's talk about odd degree, and the degree is the highest power of x. So if it's an odd degree and the leading coefficient is positive, it's going to act like a line with positive slope. So see how my equation or my graph goes from low to high, just like a line with positive slope. So if my leading coefficient is positive, that's an LC. Leading coefficient is positive, my graph will act like a line with positive slope, which means as x goes to negative infinity, so I move this direction on the graph, my function also goes to negative infinity. As x goes to positive infinity, my function also goes to positive infinity. All right, next part of odd. What if it has a leading coefficient that's a negative number? Then it's going to act like a line with negative slope. And I'm putting a blob in the middle because we could have turns, like it could start like this and then it could do this and then go back up, or sorry, that's even. And then go down. So I could start high, turn, low. All right, but we don't care what happens in here right now. We are only talking about end behavior. So that's why I put a blob, because we don't really care what happens in there. Okay. All right, so as x goes to negative infinity, so as I move to the left, what is my graph doing? My graph is going to positive infinity. As I move to the right, my graph is going to negative infinity, right? So that's the end behavior. If the degree is odd, like 5, 7, 9, 11, if the highest power is an odd number, right? What if the highest power is an even number? It's going to act like a quadratic or a parabola, right? So in its end behavior, they're either going to be both up or they're going to be both down for an even degree polynomial. All right, so first let's talk about when the leading coefficient is positive. When the leading coefficient is positive, my graph is going to act like a parabola. That's terrible. Let me get my pen to start working here. My graph is going to act like a parabola that has a positive leading coefficient. So where a is positive. So both up. That means as x goes to negative infinity, my function is going up. So as I move to the left, my graph is going up. As I move to the right, my graph is going up. If my leading coefficient is negative, as I move to the right, as I move to the left, my function's going down. And as I move to the right, my function is going down. So for even functions, my end behavior is the same. For odd degree functions, my end behavior will go opposite directions. All right, so that's degree and leading coefficient. Highest possible zeros will be the degree. So to find the degree, we look for the highest power. So that is n. That was n up here, so that's n. Highest possible number of zeros is the degree, not minus 1, it's just the degree. So if my degree is 7, highest possible number of zeros would be 7. We don't have to have 7, it has to have, it can't go over 7, okay? So if it's 7, it has to have at least 1, but the max would be 7. Highest possible number of turning points is my degree minus 1. Turning points are where my graph goes from increasing to decreasing, or from decreasing to increasing. So turning points are here where my graph changes direction. Those turning points, where those turning points happen, are also called max and mins. The highest number of those is the same number of terms. So the highest number of max and mins combined, and the highest possible turning points would be n minus 1. Every time we have a turning point, we have a max or a min. All right, so we're going to write these polynomials in standard form. We're going to pick out the leading coefficient, talk about the degree and the number of terms, and we're also going to go ahead and talk about end behavior. All right, so this polynomial in standard form, I want the highest power, and I take the number in front. So there's my largest power. So I have a negative 7x to the 6th, and then a plus 2x squared, and then a negative 3x, and then a plus 5. All right, so I'm focusing on this first term, and I see that my degree is 6, which is an even number. All right, and my leading coefficient is negative 7. So this graph is going to act like a parabola that opens down. So I know what my end behavior is. As x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, f of x, or my graph, goes to negative infinity also. So end behavior is exactly the same. All right, my leading coefficient is negative 7. We've got that. We've got the degree. Number of terms, 4. 4 terms. And we find terms by looking for the positive and negative signs to separate. I know the max number of turns is 5, and max mins combined, 5. These are possibilities. All right, let's talk about this one. This is almost in standard form, isn't it? We just need to switch places with the 8x to the 4th and the negative 6x to the 3rd. All right, so degree is 9. Leading coefficient is 4, so positive number. So this is going to act like a line and with positive slope. So blah, blah, blah. We don't really know what it looks like. We just know that the end behavior is like a line. So as x goes to the left, my function is going down. And as x goes to the right, my function is going up. Okay, number of terms, we have 3 terms. Possible turns, so terms and turns. All right, so we want to make sure we are enunciating that clearly so we know what we're talking about when we're focusing on those. So I have 9. Oh, I forgot to talk about zeros over here. I'll come back. So maximum number of turns would be 8. Max number of zeros maximum times it hit the x-axis would be 9. And this would also be my number of combined highs and lows, or maximum and minimum. So my maximum number of zeros over here would have been 6, same as my degree. Okay, so how can we use a table of values to identify key features and sketch the graph? Well, I'm looking at my x's, and my x's are increasing, so let's see what my y's are doing. From here to here, I see that my graph is increasing. And I didn't mark 3.2 because 3.2 is less than 5, so that means my graph is decreasing. Let's see when it stops decreasing. So it goes 5, 3.2, 1, negative 3, 2.6. That's moving back up. But from here to here, my graph is decreasing. Then we're back to increasing, and then we're back to decreasing. So I have a turn. It's going from increasing to decreasing to increasing to decreasing. All right, so when I'm looking at this, I see I have 1, 2, 3 turns, and I don't really know where this x value is. I just know that it's between -2 and -1 on the x-axis. And I don't really know the maximum that this gets to, but I do know that it's somewhere between 5 and 3.2. And then I know that this is taking a turn, so I'm going decreasing and then switches to increasing. Between 1 and 2, I have a minimum. And then between 2 and 3, I have another maximum because I go from increasing to decreasing. All right, so we'll be able to sketch that on the graph, but that's how I tell. Some other things that I can tell off of a table is when my function goes from a negative y value to a positive y value, I know I have a 0 or an x-intercept because it has to cross the x-axis. So anytime I have a sign change, I know I have an x-intercept somewhere between these two values. So I know somewhere between -3 and 2, -2, I have an x-intercept, and between 0 and 1, I have an x-intercept. Between 1 and 2, I have an x-intercept, and between 2 and 3, I have an x-intercept, because these values are going from positive to negative, negative to positive, positive to negative. All right, so the last thing, finding the average rate of change. Remember, that's the slope. So I want the slope on the interval from x equals 0 to x equals 2. Those are my x values, remember. I need to plug these x values back into this function to get the y value, and then I find the slope. So I'm going to leave that for you to do because that's review. So remember, I need to find f of 0, so I can put it here, and I need to find f of 2, so I can put it here. And then I can do y2 minus y1 over x2 minus x1, and I can find the slope. All right, I'll see you guys soon.